Hey everybody, so welcome to part two of our planetary geology week. This is the second lecture, but you've had a bunch of questions before on the moon's cratering history and how important that is to our understanding of planetary geology and the history of what happened in the early solar system and what's happening now. So now we're going to look at more generally at planetary surfaces and not just look at craters, although craters are a part of planetary geology, and we'll even study them a tiny bit more here as well. Okay, so here are the processes that we're really going to delve into. Impact cratering that you saw in the previous part of this lecture, and this is impacts, of course, by asteroids or comets. And the history of that crater is very important. Volcanism, so that's, as you know, the eruption of molten rock onto the surface. Doesn't have to be a volcano, as we saw for the moon. The Maria were formed by just lava seeping out of a crack in the crust. Okay, tectonics, which you've heard of, I'm sure. Disruption. This is the disruption of the planet's surface by internal stresses. So that doesn't mean that you have to have tectonic plates crashing into one another, right? As we saw, tectonics can also be wrinkling of crust and all kinds of stretching of crust that happens as the planet cools or heats up. Again, doesn't have to be plate tectonics. Okay, that's a certain type of tectonics, but tectonics is much more general. And then there's erosion, which is the surface changes you get by wind or water or a glacier moving around, right? We'll be talking about all the implications of this in this lecture. Okay. Well, we saw impact cratering on the moon, looking at that, right? And you can see here sort of a timeline. You got this little tiny thing, and it's hitting, and as it hits, it sort of blasts this big crater of material out, and you get this sort of, you can see down here at the end, you have these sort of stripes coming out. Right, so this is seen on the moon a lot. We've talked about that a tiny bit. But you can see how much bigger the crater is, about 10 times wider than the actual impact object. And small craters in general are outnumber big ones, as you might imagine. And most of the cratering happens soon after the solar system formed, and you should have figured all that out in your moon impact cratering questions that you were just answering. Okay. And of course, there's lots of impact craters all over the place in the solar system, not just on the moon. So here's one here. We've seen this before. This is Meteor crater, and you can see this. The scale here is about 200 meters, so it's quite big. But look at Tycho crater. Over here, the scale is 20 kilometers, so very, very, very big. This is one that you've probably seen and heard of many, many times on the moon. And there's different kinds of craters, and they tell you a lot about what kind of surface that the object impacted into. So, for instance, here's kind of a standard crater on the moon, and you can see very, very symmetric, like a bowl shape to it, right? But if you look over here, here is an impact into icy ground on Mars, and you can see there's kind of this like mud buildup here. There's mud flow. It's really irregular. So it really tells us a lot about the ground. And then here is an eroded crater. So you get an eroded crater that you can see there. There's evidence of some erosion from something, right? From wind or some kind of erosion. And we're going to talk about erosion more. So you can tell a lot about a crater and about the surface, actually. Tell more about the surface from what a crater looks like. Okay, now tectonics, as you know, it's not only just plate tectonics that happens, right? It can be caused by stretching of a crust or shrinking of a crust as well. It doesn't have to be a plate. So, for instance, here you can see, like when in our case, it is sort of bunching up. Most of our geologic processes on the Earth are from plate tectonics. So we have these like separate plates that are moving around and bumping into each other and doing all kinds of things. And you can see here, these are the Appalachian Mountains in our neck of the woods over here, where formed by sort of a bunching up of the crust. And these are valleys on Mars, right, that are formed from the crust moving out in the direction of these arrows, right? So they're getting pulled apart. You can see that here, a valley being formed by the crust being pulled apart in these directions. And here, of course, the crust being bunched up, you get mountains. Okay, so it's convection of the mantle that creates these stresses in the crust that are called tectonic forces. So you don't have something like this going on the moon because the moon is geologically dead. So you're not going to see this kind of process in the moon because there's no convection in that mantle that creates these stresses. Now, as we're going to see, Earth has plate tectonics, which is a whole different ball game, although it's very similar to this, but they're big moving plates. So we're going to take a look at that, and you can sort of see here from you see all the yellow is the boundary of our plates on the Earth. See, it's plates, and we're going to see a video. And they slide around on, our continents slide around on these plates. Oh, that's the wrong way. Okay, let me go to a video.
Our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust. Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on, unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental landmasses, the thinner of the two plates bends and slides under the other. As the edge of the seafloor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.
Okay, sorry about that. I had to stop an ad there. Okay, so as you can see, it's kind of complicated, right? But there's a lot going on with our plate tectonics that forms all kinds of things, like the subduction trenches that we were talking about, as those plates can come one underneath another. So a lot of really interesting crustal motion that happens due to plate tectonics. Okay. Now, what about volcanism? So volcanism, of course, is the sort of a general word for anytime you have magma shaping a landscape, right? So it could be creating a volcano. It could be creating a Maria, like on the moon. And whenever it reaches the surface, right, that's volcanism. And again, there's a lot of different ways that can happen, as we'll see. I'm going to play you a video that is looking at the plates and volcanism. But just to point out here that there's lots of kind of different ways that this happens, right? Great examples in the solar system. So we've seen already the Maria, which are kind of these pools that, the lava coming up through a crust, kind of like a break in the crust. But there's other things like shield volcanoes, where you have, so the runny lava, go back. The runny lava is what's causing the Maria, right? Because it can just sort of run out of these cracks. But if you get a little thicker, it makes these really big shield volcanoes. Like the largest volcano in the solar system, as we know, is on Mars. And that is a shield volcano. Now, if you get even thicker lava, then it really has to push up that material before breaking through because it's so thick. And it can push up very, very high and make these things called stratovolcanoes. And that's Mount Hood here on Earth. So let's take a look at this video. Sorry about that. Let me get this into full screen and then we'll play.
Where does magma originate? The Earth has a solid crust, which is thicker under the continents than under the oceans. The crust is the upper part of the lithosphere, which extends approximately 100 kilometers beneath the surface. Below the lithosphere is the asthenosphere, whose upper part is made up of a thick layer of plastic or semi-solid rock. The plates of the lithosphere rest on and slide over the asthenosphere. Magma may form where these plates meet, and here the rock cycle begins. Volcanoes are associated closely with plate tectonics. Most volcanic activity occurs where two plates meet or where the crust of one plate dives or subducts under another. A number of active volcanoes are found in parts of the west coast of North America, where the North American and Pacific plates collide. Volcanic activity is also involved in the formation of Earth's mid-ocean ridges at the boundaries of oceanic plates. As these plates slowly diverge from each other, magma rises from the asthenosphere. Iceland, an island located on top of the mid-Atlantic ridge, contains approximately 200 volcanoes. As a result, volcanic eruptions that produce large quantities of cinders and ash are fairly common. Lava from these eruptions cools to form igneous rock, building new islands. Geologists estimate that roughly 1/3 of the Earth's total lava flow since the year 1500 has poured from Iceland's volcanoes.
So you can see that plate tectonics are pretty closely related to volcanoes, or maybe the other way around. Volcanoes are very closely related to plate tectonics, although you can have volcanism, as we've seen, without plate tectonics, like on the moon. And it's unclear about Mars, whether Mars has some plate tectonics. I think recently there's been some evidence that it does have some plate tectonics, but not because we see volcanoes there, right? But we have some direct evidence from recent rovers that there is some plate tectonics going on. Now, volcanism, as we saw in the video, is really important for creating an atmosphere. So we've seen that our atmosphere really was due to this volcanism, all these gases that come from the Earth's interior create an atmosphere. Now, of course, if it just is the atmosphere released by a volcano, the elements that are released by a volcano aren't something we can breathe. But that was the beginning of an atmosphere, and then lots of other processes, as we've seen, have worked to create a breathable atmosphere for us. Most importantly, life, right? Life was very important in creating a breathable atmosphere for us. Okay, now the last process we're going to discuss is erosion, and that's kind of a little more complicated in some sense because it's a term that's about weather-driven processes, right? That do things to rock, right? So either break down rock or move rock. All right, so what are the processes that can do that? Well, there's glaciers, right? We know that glaciers move on the Earth very slowly. And as they do, they carve out rock or they transport rock as well. Rivers, as we know, like think of the Grand Canyon, and we saw there's evidence of lots of rivers carving valleys on Mars as well, and wind, which of course you need an atmosphere for, that can over long periods of time change rock. Okay, and of course also do things to other kinds of things like sand, right? All right. So for instance, erosion by water. We heard all about that before when we were talking about Mars. Thinking about how over very long periods of time, water can carve out a valley. Okay, well, of course, glaciers, like we said, can also carve rock, over a long time. So glaciers carved out the Yosemite Valley. I don't know if any of you've been there. That's where I used to go as a kid. I used to go there almost every summer. Great place to go. And that was carved by a glacier. So it can certainly to carve out rock. Now, erosion by wind is probably much more familiar because you've all seen sand dunes, and you can see it happening with your eye, right? On a windy day, you can see it shaping a sand dune, right, or a soft earth. So that's kind of a small time scale thing, right? So it's something that you can observe. Now, you can have some new features that are formed just from debris that's carried along by water or wind, right? So for instance, you can sort of see these deltas where deposited debris makes new features. So this can also happen. Okay, so we're going to start some questions, I believe. We have first question here, and then there's a lot of questions that are that are asking you about all these processes and what we know about these processes if we see any of those features on other planets. Okay, we'll start with this question. Good luck on the rest.